Let's continue talking about the set of primes in this section. Most of what I'm going to talk about will just be statements of results just to get your interest in the set of primes. And the proofs would have to be left to a more advanced class. In fact, a lot of the statements are conjectures that are major open problems still. Let's first talk about the gaps between the primes. So you have small gaps of size 2, like between 5 and 7, 7 to 11. There's a 4, 2, 4, 2, 4. And you try to look for a pattern here. 6, 2, 6, 4, 2, 4, 6, 6, 2. And if I just went that far, you might conjecture that all of the gaps are 2, 4s, or 6s, but that's not a whole lot of data. And if you went just a little bit further, you'll find that the gaps continue to grow in size. And so we might first ask, well, can these gaps get arbitrarily large? Or are they always going to be confined to some small jumps as you go from one prime to the next? And it's not hard to prove the following theorem, that there do in fact exist arbitrarily large gaps between consecutive primes. An equivalent way of stating that is that there are arbitrarily large sequences of consecutive composite numbers. So let's see how we would do that. And now I'm allowed to go out as far as I like into the sequence of integers to find this. And you may have to go very far indeed. So let's start with the number n. Well, let's try to find a gap with like n consecutive composite numbers. And the way to start here would be to take a number that has lots of factors. So say n factorial. Okay, so let's let n be an arbitrary natural number. And consider the following sequence. Where I start at n factorial, and I'll first add 2, and then I'll add 3, and then I'll add 4, and I'll go all the way down until adding n. So I've written down n minus 1 consecutive whole numbers. And I claim that these are all composite numbers. Why is that? Give me a divisor of this. Well, sitting inside of n factorial is the number 2. So 2 is a divisor of n factorial plus 2. And provided n is at least 2 in size. And that's my assumption that I stop at n factorial plus n here. How about the second number? Well, as long as n is at least 3 in size, there will be a 3 sitting inside of the n factorial. So 3 is a divisor of n factorial plus 3. 4 is a divisor of the next. 5 is the divisor of the next. And in general, if you give me any value of k between 2 and n, we would have that k is a divisor of n factorial plus k. So n factorial plus k is a composite. And thus I've got n minus 1 consecutive positive numbers. Composites. QED. All right, so that's one of the few theorems about primes that one can actually prove relatively easy. That one and the fact that there are infinitely many primes. Those are kind of the elementary results. Twin primes, big open problem in number theory today. So twin primes are primes that differ by 2, 3, 5, 5, 7, 11, 13, 17, 19, 29, 31. See if you can think of the next set of twin primes. 33, 37, 39. How about 41, 43? And the natural question is, are there infinitely many twin primes? And the twin prime conjecture is the statement that there are, in fact, infinitely many twin primes. So this remains an open problem, but there has been some recent progress. So just a couple of years ago, Zhang proved that there are, in fact, infinitely many consecutive primes, Pn and P sub n plus 1, such that the gap between them is less than a fixed constant. I'll call that gap size, the distance between the consecutive primes, the gap size. And that was done May 14th of 2000. So what size number do I have here? So he proved there are infinitely many consecutive primes within a distance of 700 million of each other. And that size has been whittled down ever since. So just a month later, we have it down to 5 million, and then down to 50,000 a little bit later that month, down to 4,400, down to 700. And the most recent I looked at the data was a result in April of 2014 by Terence Tao and Company, where the gap size had been whittled down to 246, meaning what? That meant that there exist infinitely many consecutive primes within a distance of 246 of each other. So, of course, to prove the twin prime conjecture, we'd have to get that gap size down to 2. And it's highly unlikely that that's going to be coming anytime soon. Now, just how big can the gaps between consecutive primes get? So they seem to keep popping up pretty regularly. So we proved a theorem that says the gaps can get arbitrarily large, but the real question here is, how big is the gap size relative to the size of the number that you're at? So if you just look at the data, you'll know that from 1 to 10,000, the biggest gap between consecutive primes is just 36. So if you start at any number and you march down 36 more numbers, you'll bump into a prime. And then up to 1 million, the biggest gap is 114. Up to, let's see, what's 10 to the 14th? That's 100 trillion. Up to 100 trillion, the biggest gap between consecutive primes is just 804. So if you're looking for a prime of the order of 100 trillion, you can start at any number and just test about 800 consecutive numbers, and you'll bump into a prime. So it's very easy to find primes on this order of magnitude. And you continue to see the gaps are very small between consecutive primes. Now there's a conjecture of Kramer that quantifies just how small that gap size is, and it says the following: the lim sup as n goes to infinity of Pn plus 1 minus Pn, so that's the gap size, and let's put Pn here in the denominator, divided by the square of the logarithm of the value that you're sitting at. So you're at the nth prime, and you want to compare the gap size to the size of the logarithm of the nth prime that you're starting with, that the lim sup of this is equal to 1. So what does that mean? That means the supremum of this fraction for all large values of n is less than or equal to 1. So there exists some capital N in the natural numbers such that if n is bigger than capital N, then this fraction is less than 1 plus epsilon. And this is some n that would depend on epsilon here. Okay, so in other words, the gap size Pn plus 1 minus Pn is going to be less than 1 plus epsilon times the square of the logarithm of the number that you're sitting at. So the gaps do indeed get very small between consecutive primes. Now, Cramer's conjecture is a notoriously difficult theorem to prove. Yeah, this one is, we are not even close in number theory to showing that the gaps between consecutive primes is on the order of the square of the logarithm. We can't even prove, this is a big open question, that it's even less than the square root. Right, that's a much bigger quantity than the square of the logarithm, and this is an open problem in itself. So that's a very difficult question to address. Next, let's look at the number of primes up to x. So I'll let pi of x denote the number of primes less than or equal to x. Gauss was very interested in studying this quantity, and he observed a striking similarity between the values of pi of x and the value of the logarithmic integral, the definite integral from 2 to x, of 1 over log t dt. So he just made a table, and he was able to go up to about 1 million himself, but I've continued it much further, that computers are used to get this later data. And you can see the striking resemblance between these two quantities. So up to 1 million, let's say, there are exactly 78,498 primes, and the logarithmic integral is 78,628. So you have agreement to 2 places. If we go up to this final value in the table, which is 10 billion, the exact number of primes, 45,505, 2512, has agreement with this logarithmic integral to 5 decimal places. Remarkable accuracy. And so one can see that if you take the ratio of these two quantities, this approaches the value 1 quite rapidly as x goes to infinity. Now Gauss phrased this observation in a more elegant way. So if we integrate by parts, I want to discover just, what is the order of magnitude of this logarithmic integral. So how do you integrate this by parts? I'm going to differentiate 1 over log t, and integrate dt. So you get uv minus the integral of v du. So v is t, and du, that's log t to the negative 1, so the derivative would be negative, so I put a plus here, 1 over log t squared, times the derivative of log t, which is a 1 over t, dt, and these cancel. Okay, dt is right here. So the t's cancel out, and that's still from 2 to x, And so we get x over log x, that's the main term, minus this trivial amount here, plus the definite integral from 2 to x of dt over log squared of t. And by L'Hopital's rule, you can verify that the latter integral is of smaller order of magnitude than the logarithmic integral. So if you look at the limit as x goes to infinity of the logarithmic integral, that's 2 to x dt over log t. And this is, well, no, let's show it's a smaller. Let's put this quantity up on top and the logarithmic integral down below, like that. Use L'Hopital's rule. We take the derivative of the top, taking the derivative of the integral, we just get 1 over log squared x, and this is 1 over log x. And so you get log x over log squared, which goes to 0. Okay, so the latter integral is of smaller order of magnitude than the quantity on the left-hand side, which tells me that this quantity agrees with this quantity in order of magnitude. So if you took the ratio of these two quantities, that limit would approach 1. And we express that in the following manner. The logarithmic integral is asymptotic to x over log x as x goes to infinity. And since Gauss had observed that the logarithmic integral is a very good approximation to pi of x, we get the following result, which for Gauss was a conjecture. So Gauss conjectured that the number of primes up to x is asymptotic to x divided by the natural logarithm of x. And it took the remainder of the 19th century for people to be able to prove this. The big advance in being able to prove it was work of Riemann, where he introduced the Riemann zeta function. And he turned the question of studying the distribution of primes into an analytic problem, a problem in complex analysis. And so finally, Poisson and Hadamard in 1896 were able to push through the results and actually establish Gauss's conjecture as a theorem. So it's known now as the prime number theorem, one of the most celebrated results in all of mathematics, that the number of primes up to x is asymptotic to x over log of x. Now, one of the big aims in the 20th century was trying to find some elementary proof of this. After all, the primes are part of number theory. They're just it's a question in the set of integers. So why do we need to use some deep results in complex analysis? And there was success. So Selberg and Paul Erdős did succeed in proving the prime number theorem in what is called an elementary manner, or even an elementary proof. But it's highly non-trivial. It's not at all straightforward. So it's elementary in the sense that it doesn't rely on results from complex analysis. Finally, let's mention the Goldbach conjecture, another famous open problem in number theory. It's the statement that every even number larger than 2 is the sum of 2 primes. So for instance, 10, there's an even number, is 3 plus 7. It's also 5 plus 5. 20 is 17 plus 3. How about 30? 30 is 17 plus 13, etc. So the claim is any even number can be expressed as the sum of 2 primes. And this remains an open problem. considered to have the same difficulty as the twin prime conjecture. But Vinogradov proved the following related result, 1937. Every sufficiently large odd number can be expressed as a sum of 3 primes. Every sufficiently large odd number can be expressed as a sum of 3 primes. And just a couple of years ago, Helfgott proved, in fact, that every odd number greater than 5 can be expressed as a sum of 3 primes. So he brought it down. Vinogradov, you had to have all values bigger than some great big number, and Helfgott was able to bring it down to get all numbers as a sum of 3 primes. So how does that relate to the Goldbach conjecture? So suppose the Goldbach conjecture is true. Goldbach is true. Okay, so every even number is a sum of 2 primes. And now I want to prove the Vinogradov type theorem. So I'd let, say, n be an odd number. And I want to express n as a sum of 3 primes. So, well, why don't we just subtract 3 from n? What type of number is that? So n minus 3 is an odd minus an odd. That's an even number. And so if Goldbach conjecture is true, this would be a P1 plus P2 by Goldbach, sum of 2 primes. Well, then n itself, not only can we say it's a sum of 3 primes, we can say that one of those primes is in fact 3. And I didn't have to use 3. I could have used any number right here. So you can see very plainly that Vinogradov's theorem is a weaker result, that Goldbach is a much stronger statement and implies very easily the result of Helfgott, that every number is a sum of 3 primes.